Hi everyone, my name is Vikram, and my paper for this class was Bayesian Specification Learning for Finding API Usage Errors, published in 2017 by a group of researchers at Rice University. So I'll start by giving some context. This paper focuses on bug detection, and traditionally bug detection uses formal specifications, which you can see an example of on this slide. You could see that there are particular, let's say, like classes, which with their own attributes, and then there's different like notation, like you could see some set notation, which kind of constrains how those attributes can be defined for that class. And that's what formal specifications do. They're a formal kind of mathematical way where you can define specifically what a particular software component is supposed to do. One problem with this is that it many times has to be manually done by a group of engineers, which can be time consuming, it's not necessarily intuitive, and it's not really that generalizable. You can't really scale it as your code base grows in size. And naturally, one sort of adaptation to this would be to try and learn these formal specifications. And that is its own field called specification learning. One thing which kind of aids this field is in the modern era, there's a large corpora of open source code on websites like GitHub. So there's a lot that you can train with in order to find the proper specifications. But it's still not necessarily all sunshine and rainbows. It's still kind of hard to do proper specification learnings, and the authors of this paper identified two high-level challenges. The first challenge is noise. As you have larger repos, a larger code base, there's more noise that can be introduced. In this case, some incorrect cases of code being implemented. Another thing which kind of compounds this is that traditional approaches do have a sort of binary view of what's right and what's wrong for code, i.e., this example is right, which implies that other examples are wrong, not that multiple things can be right. Now, why could this be a problem? Well, it's a problem because if you have a small number of incorrect examples, because there's this binary view, those could still be classified as correct instead of having multiple wrong cases. Now, one solution to noise would be to introduce something like probabilistic models, which weight usage patterns based off of how frequently they're implemented. And while this is good, there still is another challenge, which is challenge 2, heterogeneity. Heterogeneity is simply just the ability to invoke some like use case through like different methods. So if you want to call an API, for example, there are going to be different syntaxes to invoke it. And the thing is, it's not like there's one proper way to call an API. There could be multiple ways. And the same is true of implementing software. When you're implementing a program, there could be multiple right ways to implement it. So the thing about a lot of these probabilistic models, which kind of complicates things, is it'll only learn a single distribution, like the one on the bottom right, which is just like a bell curve. So if you have two proper ways, or two valid ways for a program to run, call them like Z1 and Z2, a single distribution model will only learn one of those, like let's say Z1, and it won't be able to take into account that there are multiple right ways to define some sort of software component. So these single distribution models aren't really robust for heterogeneity. And that's where this paper kind of has its key insight. At a high level, what the paper does is it models each of these formal specifications as their own probabilistic distribution. And you can see an example of that being done. There's like a joint probability distribution between two of them. You can see that there are like two bell curves instead of one. And that's the main insight, is that the authors combine these specification distributions into a joint probability distribution. What that allows them to do is not just learn one proper specification, but a variety, which tackles things like heterogeneity, and then also noise, because you can weight better examples more. Because this paper is in the vein of bug detection, the authors frame it as an anomaly detection problem. To do that, they define a sort of like expected behavior and an actual behavior, and in order to detect if there's a bug, they gauge the distance between them, which I'll address more later. Before we go into the framework that the authors implement, I should provide a refresher on Bayes' theorem. I'm sure all of you are familiar from this, from like stats classes, but effectively all you need to understand is like at a high level, what does Bayes' theorem actually say about hypotheses or hypotheses given evidence? Well, all Bayes' theorem is really doing is it's just asking us, given an initial hypothesis or belief, if we're given more data or evidence, how do we update our hypothesis? And that's effectively all it does. Like as new evidence, which in this case, like with the graph B, with new evidence B, you could adjust A, which is the hypothesis. And one question which you may naturally have is, how would this aid our challenges, right? How would it deal with noise? How would it handle heterogeneity? For the context of this program, if you have a Bayesian model, you can sort of like smoothly adjust your confidence in whatever patterns might be right, instead of making these very binary, this is right, this is wrong, distinction. And then as for heterogeneity, what we're doing is when you're analyzing any sort of new program, let's say you have like a set of specifications, all of which might be valid. With Bayesian thinking, if you have evidence that is more closely related to a particular program, in this case, if you have a particular program which like looks similar in its how it's like invoking a particular component to your example, then you can more closely weight that program rather than the specifications learned from the other programs. So this is all actualized through a Bayesian framework, which the authors go very in depth on. I won't go that in depth. But when we're thinking about this hypothesis evidence framing, here the hypothesis is our formal specification. It's something that's not really known explicitly. And then what is known, or evidence, is the syntactic features of the program, like the actual syntax for how, let's say, for example, an API is called. So when it comes to using Bayes' rule, all we're doing is we're using the syntactic features, our evidence, to infer the formal specification, which is our hypothesis. I should also mention that the authors also take into account things like program behavior, like how a program might behave regardless of the input data, and they utilize that. You'll see that more in the workflow diagram, which we'll go over later. Should also mention that this is just a framework, so it's not the actual instantiation of it. Salento is the instantiation of the framework. While the Bayesian framework is more abstract thinking for like any sort of component, Salento's goal, which the authors define specifically, is just to detect bugs in API calls. So you might naturally wonder, like, what are the syntactic features here, and then what are the behaviors, which I referenced earlier? The answer to that is that for API calls, the syntactic features would be just like the set of API methods being used, and then the behaviors would be the sequence of API method calls, like one after the other. So this is the workflow diagram that I was talking about earlier. You can see that there are two phases. There's training followed by inference. In the training phase, you're taking the corpus thing, like your large GitHub repository, as well as P of Y, which in this case is just an expectation of how the model should behave. It'll sort of use both of those to create a set of syntactic features and expected behaviors. And then using that, it will train a topic model. I'll go more into depth as to like why they choose to do this, why there's the words like topic, condition, RNN. But effectively, all you need to know for now is that this is what we're using to determine the distribution of expected behaviors that we want to see. And then as for the second phase, inference, you could see that we're kind of doing something similar to training, except instead of inputting a corpus, we're inputting a test program. And we still get like syntactic features, behaviors, but now it's not the expected ones. These are the actual behaviors of the program. And so now you have the distribution of expected behaviors, and then you have the distribution of actual behaviors. And by treating it as an anomaly detection problem, we use KL divergence, which is a metric you'll see a lot in like deep learning, for example, to determine the distance between these two distributions. And if the distribution lies above a certain threshold, we say that a bug has been detected. So now I'll explain the whole topic model RNN thing. Topic models, they're a tool that you'll find a lot in natural language processing. So using like ML to like analyze text. It's a model which allows you to discover hidden topics or features from large collections of documents. In this case, for the paper, they use something called latent Dirichlet allocation, which is its own topic model. I won't go super in depth, but you can see an example in the bottom right. What it's doing is it's just going to cluster API usage patterns themselves as topics. Another byproduct of this is that you're able to prevent the whole like varied styles from being treated as their own anomalies, which helps with handling heterogeneity. The second piece of the puzzle is recurrent neural networks, or RNNs. These are, I assume people know what neural networks are, but RNNs are neural networks which specifically model sequences of data, so data through time. When you have the topics and usage styles which have been pulled out by this topic model, these are inputted into the RNN. What it'll do is, given a set of topics, it'll determine the probability of the next API call sequence. You can see an example of that at the bottom. The model is sort of being unraveled into the set of like xt-1 to ht-1 to ot-1. All this means is that the model is using like hidden weights to determine outputs as each new token, each new API call is being added. And what that allows you to do is you can get an expected behavior. Like this API call was made, which implies that this one should be made after, and so on, which allows you to derive that expected distribution for how the program is supposed to act, which allows you to perform anomaly detection. So here you could see an example use case. I'll go into how Silento could be applied here. So you could see two examples of trying to implement a button, both gone wrong. In A1, you could see that the developer is forgetting to invoke a method. In particular, it's either set positive button or set negative button. And then for A2, the developer is invoking two methods, which they're not allowed to do. They're implementing, or they're invoking set message and then set view, which Android API doesn't allow. So practically, how would Silento detect that these are both bugs? Well, you'd have that training phase, if you remember from earlier, where you'd have the topic model, the LDA, which is learning from this corpus of data, like about like the proper syntax for like API calls for buttons and then messages. And then you have the RNN, which, given all of those topics, would create a proper API call sequence. So, like for example, the proper sequence for both of these would be that you create a new class for alertDialog.builder, you set the title for the button, you set the message, the text that's supposed to be inside, you do something like set positive button, and then you show it. So it would have that call sequence. And then once that's done, you'd have the call sequence, you'd compare it to the actual sequence. You'd see that there's, for both of these sample programs, there's a high anomaly score above a particular threshold. Like the KL divergence is too high, and that means that there's a bug here. So now I'll go more into evaluation. So the authors, they do a couple things. They first assess real-world specification learning using like actual corpora, and they also test the validity of the Bayesian approach versus they also have like a non-Bayesian approach which they use. And then as for specific domain focus, they test on like 3 Android APIs. I think they have to do with things like UI and then also networking. So I'll start with figure 5, which is pretty telling about like the validity of the Bayesian approach for anomaly detection. In particular, you could focus on the graphs B1 and B2, or like right there in the middle. Those are detecting things like precision and recall. Precision here is like how many detected anomalies are actually bugs, and then recall is like how many of the bugs or how many of the actual bugs were detected. In general, just going more to the top left is better, and you can see that that's what B1 does, which happens to be the graph for the Bayesian model. So what that means is that Silento is able to detect more API misuse cases, and it's able to do that while having fewer false positives, which is great. The The next graph is figure 7. This sort of addresses like the effect of increasing heterogeneity in the training data. So you can see like on the x-axis you have like the number of programs increasing. And what the y-axis is assessing is the average relative increase of anomaly score. You can see that like even when the API usage varies, like even when it scales up, the relative increase stays the same. And that's true for like the Bayesian and non-Bayesian approach. But what's important to take away is that like in general, the average relative increase is lower, which means that it's able to adapt to more usage styles, and it's also dealing with less false positives. So now I'll go over what like the limitations of this paper are. There are a couple of pretty key ones. So the first is that a lot of these results are pretty domain specific. So as I said earlier, the authors are looking at like 3 Android APIs, and that's good because Android is a pretty API heavy platform, but we've yet to see like how this approach would be adapted to, let's say, like lower level languages like C or assembly. C in particular, right? There's a lot more heterogeneity because there are a lot more ways to like effectively like effectively like define some software component. There's a lot more flexibility, and what that means is that it like calls into question, if there's less formalization, which would be the case with APIs, how well would this method work? So that's something that we've yet to see. The second, limited coverage. So as I said earlier, there's only 3 Android APIs being tested. I feel like it would be really easy for the authors of this paper to go over more, to just see how their approach scales. So that's definitely something. And then the final thing is manual bias. I didn't show it earlier, but there is a table in the paper where they have each of the anomalies, right? But the anomalies are unlabeled. So the authors choose to like manually label, this is the anomaly, which in practice, it's not that bad, but it could mean that there's some bias being introduced. Like maybe the program isn't capturing that this, like semantically, is not the actual anomaly. It's just capturing something else, some other feature. So those are 3 pretty key limitations. As for related work in this field, I kind of went over it earlier, but just to reiterate, a lot of approaches to specification learning use more rote approaches, like using finite automata or concept lattices, both of which you don't really need to know that in depth, but they both still have the problem of having this very black and white, this is right, this is wrong implementation thinking, which isn't good if you want to capture like multiple ways to implement something to capture heterogeneity. And then as for probabilistic models, you have things like neural language models. So let's say like RNNs, for example. You have models that use n-grams, which are popular in natural language processing. You have methods which use graph inference. So define the corpora you're working with as a graph to define like sequential relationships. The problem again is that even if you were to call these, they still rely on like a single distribution framework of thinking. They're not really able to account for the fact that there are multiple ways to do something right, which makes them a lot more limited than the method that these authors have proposed. So to conclude, the paper is able to provide a Bayesian framework, which allows the authors to automatically learn usage patterns. They're able to handle noise and heterogeneity pretty well. Noise because they're able to look at more specifications. Heterogeneity because looking at more specifications allows them to account for more varied use cases that may like implement the same function. They instantiate their framework through a system called Salento, and they test Salento on real-world API misuse, finding that it performs substantially better, I'll say, than non-Bayesian counterparts. As for my thoughts on the paper real quick, I thought the paper was pretty well written. I think there was a lot of math that gets kind of heavily into the weeds with a lot of like formalization, so there was a good chunk of the paper that I really couldn't go over without getting too detailed. But in general, I think the paper was good. I thought the approach was novel. It was like relatively well described. I do think there are some things that the paper is missing. Probably the most important one is some sort of analysis of like malicious actors. because something that I could see being like a real problem with this approach is that you're working with like large open source corporas, right? So you could have a case like 100% where a malicious actor chooses to upload a bunch of cases of incorrect code because maybe they want to like insert some sort of API call. So if you have enough of those being read by the topic model in RNN, it's not going to necessarily be able to distinguish that those or discern that those incorrect use cases are right if you have like enough of them, I think. So I think there is a case where you could have a malicious actor just like insert some bad code using that. And it just feels like kind of a glaring weakness. So I would wish that there's something in the paper about it. But yeah, other than that, I do think the paper is pretty well written. It goes over the evaluation well, and the limitations I appreciate. But other than that, that's pretty much it. Thank you for listening, and feel free to email me with any questions.